Okay, we're off to chapter 8 here. So last time I think we finished up nomenclature. So this will be chapter 8, which is obviously on exam 3, I guess it would be, right? Let's open that. All right, so in chapter 8 here, we're going to talk about things like atomic mass, molar mass, converting grams to moles, moles to grams, and also going to talk about empirical formulas and molecular formulas and what those guys are. So let us get into it. So the first thing we're going to talk about here in this chapter is atomic mass. And remember that as we talked about with sort of mass number or atomic number, remember that the atomic mass is actually on the periodic table. It is that number that we actually do see on the bottom of the symbol there on the periodic table. Again, remember that is not the mass number, but that is, as we'll talk about here, the atomic mass. The atomic mass is basically related to obviously how many protons, electrons, and neutrons there are. But obviously, as we talked about, atoms are extremely small, which means you can't really pick one up, put it on a balance or anything like that. So typically in chemistry and a lot of places, when you can't sort of directly measure something, a lot of times what they will do is pick something to use as a standard to compare everybody to. And that's really what they did here for atomic masses. They picked really an isotope of carbon, which is the carbon-12 isotope. And they used the carbon-12 isotope as really the standard to compare all the other atoms to. The carbon-12 isotope has 6 protons and 6 neutrons and has a mass of exactly 12 AMU, what it's referred to. So it has a mass of 12 AMU. AMU stands for atomic mass unit. It is technically one of the ways that you could take the number off the periodic table in terms of units is, for example, you could say in hydrogen, there are 1.008 AMU in an atom. And that's why you could sort of take off the units there from the periodic table. We'll talk more about a specific type of unit as to how we use those numbers a little bit differently here in this chapter. But this is one way that you could look at it. A AMU is also sometimes called a Dalton if you find somebody really old, but most people will call it AMU, and most people will not even use AMU. As we'll see later on this chapter, we could use another unit, which is grams per mole when we look at it. So 1 AMU is really the mass of one carbon-12 atom divided by the mass of 12. So basically, atomic mass, which is sometimes referred to as atomic weight, experiments showed, for example, that hydrogen is only about 8.4% as massive as a carbon-12 isotope. So really they do sort of a simple little calculation where we take basically 8.4%, which is this guy, right? Move the decimal place a couple places to the left, or divide by 100. We times it by the atomic mass of carbon-12, and we get this number here for hydrogen of 1.008. That essentially is the number that you do see, again, when you look on the periodic table there on the bottom. Similar calculations were done for obviously other isotopes and elements, and oxygen 16, obviously 5585 for iron. Now, since we did use carbon-12 as our standard here for atomic mass, when you actually do look, though, on the periodic table underneath carbon, it actually does not say 12 even. It does say something like 12.01. And there is really a reason for that. And the reason for that is what we actually do see on the periodic table are really what are referred to sometimes as average atomic masses. And what they are average atomic masses of are all the naturally occurring isotopes for that particular element. So something like carbon has like the carbon-12 isotope, also has the carbon-13 isotope, and they do occur, naturally, sort of with different abundantness. So for example, the carbon-12 occurs about like 99% of the time, about 1% of the time it's carbon-13 isotope. So what we really see on the periodic table are actually average atomic masses for all the naturally occurring isotopes for that particular element. And there actually is a formula that is used to calculate the atomic mass like we see up on the periodic table. And that formula is basically to calculate the atomic mass. You take the percent abundance, or sometimes it's called relative abundance, of the isotope. You times it by the atomic mass of like the first isotope. Then what you do is you add it, not multiply. Sometimes people always want to multiply here, but you're actually going to add it to the percent abundance, or how percent wise it occurs naturally, times the atomic mass of the second isotope. And, you know, depending on what you're dealing with, you may have 3 isotopes or so. So you basically just continue that pattern of taking the percent, again, relative abundance is sometimes referred to. And you basically could calculate the atomic mass like we see there on the periodic table for all the naturally occurring sort of isotopes. So really percentage times atomic mass plus percentage times atomic mass. Clearly, if we're looking to calculate the atomic mass for a particular element, we want to make sure obviously that our percentages do add up to 100. That means we got all the naturally occurring isotopes. Clearly, if you add up the percentages and they do not equal 100, then obviously you're missing an isotope somewhere along the way in that calculation. Any questions on that? Obviously, as well, you could convert the percentage into a decimal either by moving the decimal place 2 places to the left, or divide the percentage by 100, and it will do that for you. So you got to do that obviously mathematically wise there. So if we look at something like carbon, like I said before, really the carbon-12 isotope and the carbon-13 isotope are the two that really occur in nature. And as we see here, about 99% of the time, the carbon-12 isotope occurs, and about 1.1% of the time, the carbon-13 isotope. So we could do the calculation we just talked about. This is basically carbon-12, and that is the percentage times the atomic mass. This is basically carbon-13, and that is the percentage, obviously, times the atomic mass there in each of that. The atomic mass of the carbon-13 is 13.00. When you do all that good stuff there, you do get the 12.01 that we actually do see on the periodic table when we do look underneath carbon there. Again, most people really don't call it average atomic mass. They just call it the atomic mass, or later the molar mass. But again, they are really average values of all that naturally occurring isotopes. It's important to keep in mind that, you know, although we do consider sort of the atomic mass of carbon, for example, as being 12.01, if you were able to kind of pick out carbon atoms, you would never really find one that has a mass of 12.01. You would either find one that is basically carbon-12's mass, which is carbon-12, or you'll find one that basically is the mass of carbon-13. So for calculations and everything, we use sort of the average value, but in reality, there really is no carbon isotope that has a 12.01 sort of atomic mass. Any questions on that there? So why don't you try one here? Bromine 79 occurs 50.70% of the time and has a mass of 79.92. Bromine 81, 49.32%, has a mass of 80.92. What is the atomic mass in AMU for bromine? So first thing you would want to do, obviously, is just to make sure we do add up to about 100. In this case, obviously, we're a little bit over 100, which is okay. And then we can use our formula. So the atomic mass here would be our first isotope, which would be bromine 79. I'm just going to move the decimal place to the left there 2 places. Again, you could divide it by 100 to do so. We're going to times it by the atomic mass of that first isotope, which is 7992 AMU. We then will add it to our second isotope, which is the bromine 81. And again, if you wanted to, you could also, like I said, divide this by 100, and that will convert it into a decimal for you. And that gives us 80.92 AMU. And it looks like in this made up example here, we end up with we'll call it 8043 AMU, which is fairly close to what we do see on the periodic table, which is 7990. So fairly close to that guy there. Any questions on that there? Might have inverted a number when I made up these numbers just a second ago. Any questions on that there on the calculation part? Okay. All right, so as I mentioned before, right, atoms are very small. So one atomic mass unit, just for reference point, is about 1.66 times 10 to the minus 24 grams. That is like super small. All right. We could also use the atomic mass unit as a conversion factor. So like I said before, if we wanted to sort of pull that number off the periodic table, one way we could pull it off is as AMU per atom. So we looked up at carbon. Again, basically what that would be 12.01 AMU per atom. Or we really could write another conversion factor, which would be obviously an atom of carbon 12 would have 12.01 AMU. So if we in this problem want to calculate the mass in AMU of 431 atoms of carbon, we would start with the 431 carbons. We would get this from the periodic table and use it as a conversion factor here. The atoms will cancel out and we end up with 5176 AMU in this particular case. Any questions on that calculation there? Same thing if we went to aluminum. If we looked on the periodic table underneath aluminum, it would say 2698. Again, we really could pull off two sort of conversion factors for that. That basically means there's 2698 AMU in an atom. Or again, you could do the atom up on top if you needed to. And little dimensional analysis, 2698 AMU on the bottom. In this particular case, we are again starting with 75 atoms. So we would want to use opposites, just like doing dimensional analysis, our conversion factor here on the right, so that our aluminum atoms here cancel, leaving us with AMU. As you can see, typically speaking, when you're sort of asked to do the mass or the atomic mass, typically 4 significant figures is typically what we take it to. That's why you kind of see these answers here as 4 significant figures. And that's a good rule of thumb. Typically in this application or later on when we talk about molar mass here, whenever you pull a number off the periodic table, I might have mentioned it the other day, basically 4 significant figures is typically what you want to pull off to use in your calculations. Again, depending on your periodic table, you may see a lot more numbers underneath each of the elements for the atomic mass. So typically you want to round to 4 significant figures. Again, sometimes you may even see less numbers, like in the case up there for hydrogen, it's like 1.01, I think, which is odd, but that's rounded to 3. But most of the time, 4 significant figures is typically what you want to use. All right, so let's talk about probably a more useful way of using that atomic mass number off the periodic table, and that is what's known as molar mass and Avogadro's number. And we'll start with the mole. So the mole, which is not the furry guy, maybe it is. Let's see. The mole is basically a name that we use here in chemistry to really represent a certain amount of something. So in life, we have a lot of words that basically mean, you know, a certain amount. So if you say you have a pair or something, that represents that you have 2. If you have a dozen, that represents 12. If you have a gross of like pencils, they used to call that a 144 is a gross. So in chemistry, we actually use the word mole to represent a certain amount of something. The mole is abbreviated with MOL. I had to abbreviate it somehow, so they got rid of the E. But that oftentimes will confuse people. Sometimes people, when they see MOL, they think molecule, and that is incorrect. So when you see MOL, it is the abbreviation for mole. And basically, 1 mole of anything will equal 6.022 times 10 to the 23. So just like a pair is 2, a dozen is 12. If you say you have a mole of something, that represents that number right there, 6.022 times 10 to the 23. The units that actually go with that number, which as we'll see here in just a second, is what's known as Avogadro's number. The units that go with that can really be anything. It could be, you know, particles. It could be atoms. It could be molecules. It could be pizzas. It could be shoes. Probably more so in chemistry. These two will be the 2 very common units that you will see go with that number, which are atoms and molecules. But technically, it can really be any type of unit associated with that number. So if I say, for example, I have 1 mole of hydrogen, that means I have 6.022 times 10 to the 23 atoms of hydrogen. And you could use it for something that's just like an element by itself. You could also say, for example, if I had 1 mole of water, H2O, I would have 6.022 times 10 to the 23 molecules of water. Here we use the units of molecules because water is a molecule. Before there, we use hydrogen, which is just an atom, as units of atoms. So again, that sort of units sort of change, number stays the same. You pretty much could take anybody from the periodic table and say if you have 1 mole of it, you have 6.022 times 10 to the 23 atoms of whatever element it is. And any molecule, same deal. That would be how many molecules you would have. Any questions on that there? As I mentioned before, this is Avogadro's number. Avogadro's number. Something like that. So 1 mole is 6.022 times 10 to the 23. What do we use this for? We really use Avogadro's number as a conversion factor to go between those units, the units of moles and molecules, moles and atoms. So we really use this to go between moles and atoms, our molecules, and back, basically. Where obviously we could do 1 mole of something up on top, 6.022 times 10 to the 23 atoms on the bottom, or 6.022 times 10 to the 23 atoms on top, 1 mole on the bottom. So this is really your conversion factor of when you're trying to go from, in most cases, molecules or atoms back to mole, or vice versa, moles to either molecules or atoms. People oftentimes will use Avogadro's number everywhere because they're like, hey, I learned that number. I probably should just throw it down on every calculation I do. And you really shouldn't do that. So you should only use really Avogadro's number if either you are given a number that's in atoms, molecules, particles, or something like that, or you're asked to find something in atoms, molecules, or particles. If it really doesn't mention any of those things, you should really leave Avogadro's number on the side. I've seen people use like Avogadro's number in the front of the calculation, and then luckily use it in the back. It cancels each other out. They divide by 1 and multiply it by it later on. But don't use it anywhere. In every situation, it does need to be one of those sort of situations, atoms, molecules, or something involved there. So like I said before, 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. Again, if you had 1 mole of CH4, that would have 6.022 times 10 to the 23 molecules of CH4. Again, here, CH4 being a molecule, we use the units of molecules on this guy. All right. Now, the other sort of conversion factor that we use a lot in chemistry, and it sort of is related to what we were just talking about off the periodic table, is what is known as molar mass. And molar mass is a really important sort of conversion factor that we use in chemistry a lot. And molar mass has units of grams per mole. So those are the units that are associated with molar mass. And basically, numerically speaking, the atomic mass of an element off the periodic table that we just talked about in AMU per atom is numerically equal to grams per mole. So how we usually will pull off the information from the periodic table is we really won't use AMU all that much, but we will use it as the molar mass. So if we looked at carbon, basically 1 mole of carbon would have 12.01 grams. And we could write the molar mass of carbon as 12.01 grams per mole. And you really could use it as a conversion factor. So if you needed to, you could flip it around and put the moles up on top and the 12.01 grams in case you need to divide by it. But if you were asked what is the molar mass of carbon, it is this one right here, 12.01 grams per mole. The number always stays with the grams part. It's always per 1 mole when you do it. And really, molar mass is our conversion to go from moles to grams and grams back to moles. And that is a calculation we do a lot in chemistry. And we don't have to just get the molar mass of, say, one element. Earlier, for example, we had something like water. If you need the molar mass of water, you basically just add up all the parts. So there are 2 hydrogens at 1.008 grams per mole from the periodic table, plus 1 oxygen at 16 grams per mole. That means that the molar mass of water is 18.02 grams per mole. So if you need the molar mass of a molecule or something like that, kind of like we were talking about, I think with our hydrate last week, you basically add up all the parts of it from the periodic table. Again, pulling off the number with 4 significant figures is typically what you take off the periodic table and you add it together. So the molar mass of water would be 18.02. Again, you really could use it as a conversion factor where the number stays with the grams, as I just mentioned, 18.02 grams per mole. Or you could put the mole up on top and use 18.02 grams on the bottom. So again, really molar mass, a conversion factor. Where we get the conversion factor is from the periodic table, and it allows us really to do a very important calculation, which is to go from grams to moles or moles to grams. It's really important because when we weigh something out, right, it is in grams, right? We don't usually go over there and figure out how many moles on the scale or anything like that, or how many AMU or anything like that. So this is a very convenient way to get us to a number where we could perhaps measure out something in terms of mass. Any questions on molar mass there? So I would say that probably for the most part, you will use molar mass way more than you'll use Avogadro's number. It will pop in occasionally, obviously in this chapter and stuff like that. But outside of this chapter, molar mass is used a lot more, I would say, in most calculations than sort of Avogadro's number and stuff like that. All right. So as I mentioned before, there is a relationship, and I think we just saw it there. That's like 1.9 times 10 to the minus 23 grams per AMU. It's a very small number, obviously. So that's okay. You guys worry too much about those. All right. So Avogadro's number, like I said, and molar mass are really conversion factors. Where we will go from one unit to the next. A good way to kind of do those calculations is sort of a dimensional analysis approach where you can kind of see the units cancel and figure out everything. So let's take a look at an example here. How many moles of helium are there in 5.46 grams of helium? So why don't you give it a go? Again, if you were to look up helium there on the periodic table, it will say 4.003. All right, take a second, see what you come up with. Okay, let's take a look. So first question is, do we need to use Avogadro's number here? And the answer is no. We're looking for moles. We're given grams. There's no mention of atoms, molecules, or anything like that. So this is really a sort of grams to moles conversion. And that is our molar mass that helps us do that. In this case, since we are looking at helium, we could just simply go to the periodic table and pull off that number, which means that there are 4.003 grams per mole of helium, or again, you could kind of do it the other way there. So here we could just a dimensional analysis here. It is 5.46 we would want to start with. Grams of helium. Again, opposites cancel, which means we do want to use it like so. 4.003 grams per mole of helium. The grams will cancel each other out. And looks like maybe a 1.36, I think. And that would be 1.36 moles of helium. Any question on that calculation there? Okay. They agree with me, so that's good. All right, let's try another one here. I feel like you have this one next, maybe. How many, we'll go with this one next. How many grams of zinc are there in 0.256 moles of zinc? Again, if you go to periodic table underneath zinc, you will see 6539. Unless you look on these new fancy periodic tables where they change the mass after all these years. Okay, so same thing here. Looking at this, we're looking for grams. We're given MOL, which again, a reminder is moles, not molecules. So again, no mention of molecules, no mention of atoms, no need for our Avogadro's number here. So we do again need the molar mass from the periodic table. And again, that number means that there's 6539 grams per mole of zinc. Or again, if you needed to, you could flip it around and use it like this. Starting with what was given to us, which is 0.256 moles of zinc. Remember, opposites will cancel. So in this case, we will go with the one here on the left. And that would get us 6539 grams per mole, where our moles will cancel, yielding us about a 16.7 grams of zinc in this case. So again, if you were asked to measure out 0.256 moles of zinc, you should get about 16.7 grams of it to get the correct amount. Any questions on that calculation there? All right. So let's try a couple more here. How many moles are there in 23.2 grams of ethanol? How many molecules are there in the same? We'll give you some periodic tableness in case you don't have. Carbon 12.01, hydrogen 1.008, and oxygen 16. Here, so first question is how many moles are there in 23.2 grams of ethanol? And how many molecules are there in 23.2 grams of ethanol? So if we take these individually, what we got going on here is the first one, we got grams and we want to go to moles. So remember, the first one really is just a grams to moles, and that is the molar mass that we need. Again, to get the molar mass, we simply take the formula, we go to the periodic table, basically just add up all the parts. So in this case, there are 2 carbons, each at 12.01, plus 6 hydrogens, each at 1.008 grams per mole. And there are 1 oxygen here at 16 grams per mole. So this is basically our carbon, our hydrogen, and our oxygen here. Doing all that together there will give us the molar mass of this guy here, which would be 2 times 12.01 plus 6 times 1.008 plus a 16, looks like a 4607. That number is how many grams there are per mole. And again, we would use that as a conversion factor here. So we would start here with 23.2 grams of C2H6O. Using the molar mass that we just calculated, we want grams to go on the bottom so that they cancel. So that would be 46.07 grams per mole here. And that gets us 23.2 divided by 4607. We'll call it 0.504 moles of C2H6O here. Any questions on that part of the calculation? Yeah. Yeah, so typically, like I said, when you calculate something like this and you kind of pull those numbers off the periodic table, it is customary to sort of end with 4 significant figures is typically what you want to end it with in most cases, yeah. And same thing when you pull the numbers off the periodic table, you could just use sort of the 4 significant figures to calculate it as well. Like I said, some periodic tables, they'll give you a ton of numbers and some will give you not so many, but 4 is usually the common rule that you want to go with. And then in terms of the calculation part, still sort of sig fig wise here, we really would be going off the sig figs off of this number here, the first number, as we would kind of think of the molar mass as almost like an exact number. Yeah. Other questions on that? At this point, we can now sort of do the second part of the calculation, which is we want to know how many molecules there are in the 23.2 grams. Really, the path, if we were just given this question, would be we need to go from grams to moles and moles to molecules. And since we sort of did this first part above, we could actually pick up from that part of the calculation to do it. Now, in this case, we are looking for molecules. So that's the keyword that we do want to use Avogadro's number here. And Avogadro's number, again, being the 6.022 times 10 to the 23 molecules per mole. And we'll just pick up with our number we got above, which is 0.504 moles. And we actually would want to use Avogadro's the way I just wrote it. Moles would go on the bottom. Avogadro's number here would go up on top. And again, the units here would be molecules, as C2H6O is a molecule. We also want to make sure that we do use our exponent button, obviously, when we put in Avogadro's number, and we should end up with something 3 point, looks like 04 times 10 to the 23 molecules of ethanol. Any question on that calculation? Is that a small amount or a large? That's a really large amount, right? So there's a ton of individual ethanol molecules floating around in that 23.2 grams of it, right? Any questions on either of those calculations? Again, if you were given just the bottom question, which was how many molecules there are in the 23.2 grams, you could have just did this all in one big calculation, obviously starting with the first calculation and rolling into the second, or like any other sort of conversion, you could just get an answer and continue on as well. So whichever way you want to do it. All right, so why don't we try this? What is the mass in grams of 1 molecule of caffeine? For the mass in grams here, and of 1 molecule. So in this case, we do see the word molecule, which means I should use Avogadro's number somewhere along the way. In this case, we're actually starting with molecules. So the kind of pathway there is we want to go from molecules to moles using Avogadro's number. We then can go from moles to grams using the molar mass to do so. So that's sort of the pathway you want to take. In this particular case, we will need the molar mass, so might as well calculate that up front. So that is 8 times 12.01 for our carbon, plus 10 times 1.008 for our hydrogen. That is then plus 4 times 1401 for our nitrogen, and lastly 2 times 16 for our oxygen here. That's a lot of numbers there. So 8 times 12.01 plus 10 times 1.008 plus 4 times 1401 plus a 32, about 194.2 grams per mole here. So again, we're going to need that obviously on the back end here of the calculation. We will start with our one molecule of caffeine. Here we will use our Avogadro's number to convert it. And we want the Avogadro's number here on the bottom. So that is going to be 6.022 times 10 to the 23 molecules per mole. At this point, if we stop the calculation right there, the molecules will cancel. We'll be left with moles, which again is close to what we want. Now we can basically do this last conversion here, moles to grams, using the molar mass that we just calculated. Again, if you wanted to, you could get an answer at this point, or you could continue obviously with the calculation. Moles are up on top, which means in order for them to properly cancel, moles do need to be on the bottom, and the 194.2 grams need to be up on top so that they do cancel. And that looks like, here we go, 194.2 divided by Avogadro's number. Looks like 3.225 times 10 to the minus 28 grams of caffeine in this particular case. Any question on that number? In terms of significant figures, if that's a question, is basically we started with one molecule, which technically would be something you would be counted. So you really could give the answer to any amount of significant figures in this case because of that. Any questions on any part of that? Yeah. No, so it's Avogadro's number. So it's sort of like a constant that is, you know, that 6.022 times 10 to the 23 is basically the number that you use every time you would use obviously Avogadro's number. So yeah. The molar mass you do typically need to calculate, you know, unless it's just like one element by itself, then you just pull the number obviously off the periodic table. But if it's some type of molecule or something like that where there's more than one atom involved or element involved, you do typically need to calculate the molar mass. Other questions? Questions on molar mass, Avogadro's number, how to calculate these things? Again, calculating grams to moles, moles to grams, you do a lot. So that molar mass from the periodic table, very important calculation. Let's talk about one aspect of this as well. Let's just say we had our, let's say we had our 25.5 molecules of C2H4O, and we want to know how many grams of carbon are there. So this is sort of a variation of doing some of these calculations. In this particular case, we are not interested really in the end of the whole entire thing. We're just interested really in the carbon part of it. And we can do that using some of the calculations that we just talked about. So first off, though, we can actually use our formula here as a conversion factor, and something we'll talk about here in a bit in this chapter, which is when we look at the subscripts that are on the bottom here. These can represent the moles of each of those sort of elements that are involved. And we actually can write some conversion factors from the actual formula itself. For example, we could say in 1 mole of the entire thing, there would be how many moles of carbon? It would actually be 2 based on the formula. We could also say in 1 mole of the entire thing, there are 4 moles of hydrogen. And again, that is just the little guy on the bottom there. And obviously in 1 mole of the entire thing, we could say there is 1 mole of oxygen. Again, obviously the number that would be there if it wasn't 1. So in this particular case, because we want to actually end up with just carbon, not the entire thing, we could actually use the actual chemical formula as a conversion factor to do so. The rest of the calculation is sort of similar to what we would do. So first off, obviously, we see molecules mentioned here. So we need to go from molecules to basically moles. And we need to do that because that is what's going to allow us to go from the entire thing in moles to moles of carbon. So the first part of the calculation we would do very similar. We would take 25.5 molecules of the whole thing. We would use Avogadro's number, 6.022 times 10 to the 23 molecules per mole of the entire thing. And that would get us, in this particular case, 4.23 times 10 to the minus 23 moles of the entire thing. So this conversion, very much like what we did before, that is going to allow us, as I mentioned, to now use our conversion that we got from the formula to go from moles of the entire thing to just moles of carbon, which is what we're interested in here. So if we did that, 4.23 times 10 to the minus 23 moles of the entire thing, and 1 mole of the entire thing, there are 2 moles of carbon, which would get us 8.47 times 10 to the minus 23 moles of carbon. So using the actual formula, we were able to go really from moles of the entire thing to just moles of what we're interested in. And in this case, we now can figure out that there are 12.01 grams per mole carbon. The moles of carbon would cancel. That's the molar mass of carbon. And we would times it by 12.01, gets us approximately 1.02 times 10 to the minus 21 grams of carbon. So a variation of sort of molar mass, grams of moles, molecules, is sometimes you're not necessarily interested in the entire thing that's given to you. You may be interested maybe in just the carbon part like this. We obviously could do a similar calculation for hydrogen or oxygen. And you could actually use the formula itself as a mole to mole sort of conversion factor to allow you to go from the whole thing to an individual element that's involved. Any questions on that calculation there? So that is, again, a very also sometimes pops up, 1 element versus the whole thing. Use the formula as a multiple relationship. Any questions on that one there? Okay, then what we're going to talk about next is, speaking of formulas, we're going to talk about some different types of formulas and a couple different ones. Let's take a look here. Maybe, there you go. So the first formula is what is known as a molecular formula. As we talked about before, a molecule is really a combination of 2 or more atoms together. They could be 2 of the same element, different elements. A chemical formula really expresses the composition of a compound in terms of a symbol. The molecular formula pretty much tells us exactly what is present. So when we do see a molecular formula, it's exactly what is present. So for example, CH3COOH, C2H4O2. Both of these are molecular formulas. There are actually molecular formulas for the exact same thing. They're both acetic acid, which is vinegar. One formula gives you a little bit more information about how it's actually connected. The other one just kind of tells you what is there. If you drew again, acetic acid, it looks something like this. And you can see that this formula, CH3, CH3, CO, CO, OH, OH, gives you a lot more information about how it's really connected and put together. But this is really a molecular formula, basic molecular formula that just tells you what's there. It obviously doesn't give you any type of structural information about how everybody is connected to each other. And sometimes, a lot of times, molecular formulas are like that. They're just the basic, these are the elements there and how many. And sometimes they do give you some structural information. So as I mentioned, the molecular formula really is the basic formula that tells you exactly how many elements you got going on there. The simplest type of molecules are diatomic molecules, and something like H2N2 are their molecular formulas. In their simplest form, as I mentioned on the previous page there, it just gives you the information that's there, as opposed to these two here. So again, that is a molecular formula. That is a molecular formula. But again, this is ethanol, and this gives you a little bit more information about how it's put together. But if you count up all the elements, 2 carbons, 6 hydrogens, and 1 oxygen in each of them, so they do represent the same thing. Sometimes confuses people when they look at labels, how the molecular formula is written, and is like, I don't recognize that because it's just like the basic, C2H6O. So a lot of times they will write it a little bit more structurally to give you that information. Now, that is different than another important type of formula, which is known as the empirical formula. And the empirical formula is the basic, simplest representation of what is present. So it is basically the simplest whole number ratio of what elements are present and what atoms there are. So for example, if we looked at hydrogen peroxide here, H2O2 is basically 2 hydrogens for every 2 oxygens. That is the same as a 1-to-1 relationship. So the empirical formula would be 1 hydrogen and 1 oxygen, 2 H2O2. Same thing if we had C2H4. This is basically 2 carbons for every 4 hydrogens. You could actually reduce it down by 2 and get an empirical formula of CH2, which would be the simplest whole number representation of what is present. Now, in terms of empirical formulas, all ionic compounds are empirical formulas, because if you think about how you properly put together an ionic compound, positive and negative guy, you want to equal 0 in the simplest way possible. So when we look at any type of ionic compound in terms of their formula, they're always in the empirical formula, because they should be put together in that simplest way. Now, sometimes the molecular formula and the empirical formula are the same. So if you took something like water, H2O, that is again 2 hydrogens for every 1 oxygen. That is basically as far down as you can go. You can't reduce it down anymore to get whole numbers. And that means that water is both the empirical formula and the molecular formula is the same in that particular case. So if you have a molecular formula that you can simply reduce down by a common number, if you have a molecular formula you can reduce down by a common number and still obviously achieve all whole numbers, then you could write the empirical formula for it. Any questions on the two? Empirical formulas are typically the formulas experimentally that are found, because they're very easy to sort of find by just doing simple mass measurements and stuff like that, and doing little divisions to get the simplest sort of whole numbers that occur. So here's a couple of other examples here. N2H4, again, That's the molecular formula. That is 2 nitrogens for every 4 hydrogens. Again, you can basically reduce everybody down by 2. Gives you 1 nitrogen and 2 hydrogens, which would be our empirical formula for it. It's important to remember that it is only the molecular formula that actually does tell you the exact amount of atoms that are really there. The empirical formula, again, is just that simplest representation of the whole number ratio of what is present, but not exactly the number of elements and atoms that are present. All right, I think we will lay it up there for now here.